Dear participant of our conference, I presented the best plenary speech to this day, conference day. Professor Igor Chalenko, and speech with the title Statistical Learning for Stochastic PDE Models. Please.
Florin, mulțumesc frumos. Deosebit plăcere să iau parte în conferința asta. And I guess I have to switch to English at some point. So again, thank you very much for the invitation to the organizers. This is like my honor, honestly, my honor to be present at this conference. Unfortunately, not in person, a couple of weeks earlier, and I would be there, but well, hopefully next time. Needless to say that, of course, the Moldova State and the Institute has a very special part in my heart. So thank you very much for having me here. I'll talk about the statistical learning for SPDs. And I'm not listing any co-authors, but you'll see that I have a bunch of collaborators on this long-standing topic that I've been working for some time. When I say a PDE, I mean an SPD, I literally mean a PDE plus some random noise. And in contrast to having random coefficients or having random initial data. So the equations that I'm going to work with are parabolic, linear, or nonlinear. So the simplest one would be, for example, heat equation. One derivative in time, two derivatives in space, and some noise. The noise that I'll take will be always something which is Gaussian, although that would be in a Hilbert space. Now I'll have, again, it's a public lecture, I'll make some things very kind of naive and simple, so I apologize to the experts. I'll have time, space, x, and omega will be randomness, which I'll usually not write out. So why to bother with these SPDs? The SPDs have been around for some quite time. Now they are well understood from an analytical point of view. They come as models. First of all, that's clearly any PDE that you have in mind. Well, propagation of heat, wave equation, transport equation, anything that is a PDE may have a misspecified as a model, which means maybe random measurements with random noise. Could be just because you pass to the limit from microscopic to macroscopic level. Could be a product of another problem. And filtering is one of those examples where you have a signal and then you observe a signal plus noise. When you try to filter the signal, the solution to that density would be the Pi equation, which is in SPD. It could be just a reasonable model, and randomness comes naturally from the underlying model. That's typically in finance and economics. So there are enough applications to consider, and they are real life applications. But also as a mathematical tool, it's interesting actually to look at these objects. So what I'm trying to solve is, what is the problem? The problem, general problem that we are trying to solve, it's a statistical problem. We observe, let's say we have this heat equation, okay, with some coefficients, theta and sigma, colored here in red and blue. I'm not going to call them, viscosity or diffusivity or something, not to confuse it with those from diffusion processes, but theta in front of the Laplacian, sigma in front of the noise. It is somewhere. This is I'm not specifying what is G, what is the domain. Could be full space, could be bounded domain, could be an RD. W is a noise. It's a Gaussian noise, and I'll show you a little bit more what is this noise. What I observe the solution U. One path, one realization of the solution. Somewhere, perhaps on continuously in time, perhaps continuously in space, maybe a projection of the solution, maybe discretely in time. I observe something about you, and I'll be more specific what I'm observing. So observations are either in physical domain or maybe in the free space, and I am trying to find an estimator, as in statistics, to find an estimator of theta and sigma given those observations. How do we do that? And what is most interesting actually in this field for myself is that at the intersection of PDE, stochastic analysis, statistics, real analysis, and it's a combination of all of those. And I hope at least, to give you a hint that indeed this is true. So, again, for general audience, let me start a little bit, at least to show you a couple of pictures, what is going on here. I still assume that, from undergrad PDE class, we know how the heat equation looks like and what is the noise. So one-dimensional noise, the classical Brownian motion thing, is, of course, it's a process. The two realizations of the path are in this picture. It's a Gaussian process, which means that the paths are continuous. The independent increments, the stationary independent increments, and the increments are normally distributed. Equivalently, of course, since it's a Gaussian process, it's enough to specify the covariance structure. Or if you wish, you can look also at a Brownian motion as passing to the limit of a random walk, symmetric random walk. Now, what happens? And again, this is the thing that goes back more than 100 years ago. Now, what happens if we have a PDE or an SPD? Of course, the elements of these equations are in are functions. They live in some Hilbert spaces. So I'll need to define properly what is the Brownian motion in a Hilbert space, or a cylindrical Brownian motion, or a Brownian motion valued, let's say, in L2. There are several ways of doing that. But essentially, since this is a Gaussian and continuous Gaussian process, it's enough to specify, again, its covariance structure. And for the space-time white noise, which means it's white, it's fully noisy in space and in time, that would be the covariance structure. Square brackets are the inner product in L2. The way I like to look at the noise in L2, and Brownian motion in L2, is take a base in this Hilbert space, let's say sine of kx, or any base you like, multiply each element of the base with a one-dimensional, 1D linear process, the one that I showed on the previous slide. Of course, you sum this up. Whatever you get would be the cylindrical Brownian motion. Sure, this series may not converge, actually does not converge. You need to define properly what is this convergence, what kind of elements, in what kind of spaces, and make mathematical sense out of this animal. But that are technicalities, and this is done. Pretty much similarly to how you define a solution to a PDE. The bottom line is here that this object is infinite dimensional, lives in L2, and it's a proper noise in every direction that you have in the base. So this is the realization now of one of these noises on time from 0 to 1, and x is from 0 to pi, and that's the noise, white noise in 1D. That's the heat map of the same noise. So now if you take a PDE plus this noise, the picture will look something like that. So this is exactly heat equation, theta constant, sigma constant, on the interval, zero boundary conditions, zero initial data, and it is from 0 to 1. Time runs from 0 to 1. It's quite noisy, but there is some structure there. So that's how heat will diffuse. Now, that's more or less also the observations that I have, and I'm trying to estimate theta and sigma. More pictures to give you an idea how things look like as far as the solution. So this is the heat equation, the first row. Now this is with multiplicative noise, similar noise. You can see that the heat started from something which is probably sine, and then propagates and diffuses in time, but it's random. So in contrast, again, if you would take a deterministic PDE, deterministic heat equation, everything would be C infinity smooth. You'll not have these jiggles over there. These are nonlinear equations. So Alan Kahn, and this is Berger's, or 1D Navier-Stokes equation. So those are my observations. I'm trying to find this theta. So the statistical inference for SPDs has some history. It's not something that we invented overnight. For most of the part, we've been doing spectral approach, so-called spectral approach. So what is that? We shift the observation scheme and say that the solution is observed in the Fourier space, okay, continuously in time. That means that we assume that we observe the Fourier coefficients of the solution, same as separation of variables in the PDE. So we make the observations in the Fourier space. Now, those models are singular, statistically speaking, but they can be approximated with a sequence of regular models. So what that means? That means that if we look at that system, which is an infinite dimensional system, do a Galois projection, you get a system which is an n-dimensional system, n-dimensional n equations, n diffusions, and then you can use the tools from statistics for stochastic processes. In particular, you can use maximum likelihood estimators or radon-equative derivatives. You can do math there, you can do statistics there, and prove that actually you can estimate, and there are estimators which are consistent and asymptotically normal, as number of Fourier coefficient increases. And there is a plethora of papers written on this subject. Today, I decided to talk somehow more about these recent results that we have on sampling in physical domain. And I'll be more specific. That means that we literally observe the solution itself, assuming it's a function, that we observe the solution somewhere in space and time, but discretely, not continuously. There is another method that we've been also working is local measurements, initiated by my friends from Humboldt University, but that's a different topic. I actually also run a website called Stats for SPD, that collects all the bibliography on this topic. It becomes now, in the recent 5-6 years, there are several schools now working on this topic. So to give you a flavor how things have been developing, this is the literature and also more or less the history of this topic, of the spectral approach. As I said, these are measurements in the Fourier space. I wrote a couple of years ago a survey paper detailing how things are done for those who are interested in. We've done fractional noise, multiplicative noise, hypothesis testing, trajectory fitting estimators, Bayesian approach, nonlinear SPDs. This is probably, for people coming from PDE side, you can appreciate probably that. And the recent one is still in the production. We treated the stochastic primitive equations, which is a simplified version of the 3D Navier-Stokes equations, where really we use the structure of the solution to prove the consistency and asymptotic normality. So now, how about the discrete time sampling? So in this setup, things are quite different. The problem has been open for quite long time. I mean, first time I heard tens of years ago, and then after some struggle, we made first progress, and these are the two papers proved in parallel by quite two different methods. Started somewhere in 17, but we proved it in around 20, and then things started developing fast, and there are now more papers on that. And I'll try to give you the idea that we had, which is different from my friends that did a slightly different approach. We use the regularity of the solution, and regularity as in classical analysis, how many derivatives we have there, and we choose the correct power variation, and that allows us to actually develop estimators, consistent estimators. And if I'll have time, and I hope to have time, I'll show you some results, some recent results, where we show the power of the analysis sort of combined with statistics. So back to my heat equation, and once we understand this, things will at least become a little bit clear what to do. Again, I'll take heat equation, stochastic heat equation, space-time white noise. And as I said, it's convenient to look at the space-time white noise written in this form. Why sine kx? There are a couple of reasons for that. First of all, sine kx on L20 pi is a base. It's a complete orthonormal system. Secondly, it's also the eigenfunctions of this Laplacian. Okay? And that is helpful because then the projections will commute. I'll take zero initial data, zero boundary conditions. And first fact that I'd like you to remember is that this solution U is, first of all, exists, is unique, and is also continuous, has no derivatives, and it is 1/4 Hölder continuous in time and 1/2 continuous in space. This minus means almost. I mean, Hölder continuous up to degree 1/4 and 1/2. That's not hard to prove these days. That's typically now an exercise in a graduate level class for SPDs, using Kolmogorov criteria, for example. But that gives us a hint of what to look at. For example, the Brownian motion, one-dimensional Brownian motion, will have Hölder continuity index 1/2. Okay, so that's another fact that I'm gonna use. So what is this good for? And how much we can do. It turns out that to estimate this parameter, you don't need to observe much of the solution. There is enough information in observing the solution, either fixing time, that's my scheme A, fixing time and sampling discretely in space, or fix space and sample discretely in time. The picture is probably easier to digest. These are one scheme, this is another scheme. And we also claim that these are minimal assumptions, that minimal sampling schemes that you can have for these solutions to identify those two parameters. Well, one of them, assuming the other is known. Okay, so I fix time, and I sample a little bit in space, doesn't matter where. And as more data is sampled from this fixed interval, I get consistency, asymptotic normality, and vice versa. You just freeze one point and measure the solution there on a very small interval of time. And the more you sample the solution. Yeah, you can, of course, go and have more information. You'll sample discretely, both in space and time, and you'll get better estimates. But that's a different story. Okay. So, how do we proceed with this? We start from. Let me recall at least what is the variation, and this is power variation. For people in stochastic analysis, of course, this is sort of the basic tool that we work with. For others, well, the variation is just the sum. You take a function or a process in my case, you take the sum of the increments, absolute value of the increments, and you pass the limit as the mesh or the delta t goes to 0. Now, if the function has more than one derivative, then that variation exists, and it's a bounded functions of bounded variation, for example. Now, my functions, my processes typically are noisy, so they are not. Brownian motion is not having derivatives. It's Hölder 1/2. That will not have finite variation. But it may have, the rougher is the path, the higher p variation you can take. And it turns out that also it's not hard to prove, obviously, that to have only one p for which this limit of this sum would be non-trivial, non-zero, not infinite. Okay. So for Brownian motion, the right thing to look at is the quadratic variation, and I'll have it in a second. That. Now, what is that p for now? It's a number such that this limit exists. In some sense, it's either almost surely or probability. Doesn't matter for now. Okay, so first result that we show, and as I said, this power variation, it's a good way to look at, is that the power variation somehow captures how rough is the one path. And the rougher, the less continuity we have, the higher p we can take. Now, naturally, one would expect that if I make a perturbation by a smooth process, so if I take a process x or a function x and I add something smooth, the power variation should not change. And this is indeed true. So first result is that the smooth perturbation will not change the power variation. Intuitively clear, possible to prove. Not only that, we also can show that if this limit, if the power variation is a limit, if this limit exhibits some sort of, so this approximation of the variation is VPN, it exhibits some central limit theorem, which means there is a convergence in law to a central Gaussian random variable with some rates, then a perturbation will obey the same convergence. In other words, I have consistency here, an asymptotic normality. And with some additional assumptions on why we can go to the threshold of P taking the quadratic variation and so on. Okay, so the bottom line here is that smooth perturbations do not change the quality of do not change, first of all, the variation, and also do not change the convergence result. Now, let me illustrate you how this idea actually works for Brownian motion. And again, that similar ideas, of course, we teach when we teach the stochastic analysis class. We teach about the quadratic variation of a Ito process and how that plays, for example, to estimate, I don't know, the volatility or the diffusion in simple diffusions. So imagine I have a process Z such that this Z is equal to a Brownian motion B times an unknown coefficients root of beta plus something smooth. And I observe Z. Of course, I don't observe B, I don't observe Y. And I don't know beta. Now, let me take quadratic variation. Why quadratic? Because B, being a Brownian motion, will have a quadratic variation over there. And then, respectively, if I take the quadratic variation, I'll have that quadratic variation of Z is the same as quadratic variation of root of beta B. Y doesn't change it. And that would be equal to beta times B minus A. Why B minus A? Quadratic variation of the Brownian motion is exactly the length of the interval. And that means beta is equal to quadratic variation divided by B minus A. I can approximate it by a sum. And here we go. I found an estimator, a simple estimator in 2 lines for the coefficient beta. Okay. So not only that, there are well-known results on central limit theorem for the quadratic variation of the Brownian motion. And that means I also have asymptotic normality, so more central limit theorem for this estimator. So what did I do? I found a simple way to actually estimate beta if I observe the entire thing. Now, how that translates to my SPD? So, and this is what we noticed, and that was sort of the starting point. Remember that I said that if the solution is 1/2, 1/4 continuous in time and space. So if I fix time as a function of x, this is 1/2 Hilbert continuous. Same as Brownian motion. Brownian motion is 1/2, and that's why for Brownian motion I have quadratic variation power 2. Well, maybe this u, as time is fixed, is something that like a Brownian motion plus something else. And it turns out that indeed, and this is a result, an interesting result in itself, indeed, because of the structure, because of Gaussianity, you can show that although the solution is quite complicated, it is equal to a Brownian motion, one-dimensional Brownian motion B, times a coefficient plus something actually with C infinity smooth. All right. Not only that, the coefficient in front of this Brownian motion is exactly sigma and theta that I'm interested in to estimate. So these are parameters of interest. Or precisely the ratio I will estimate, or one of them knowing the other. And this result now obviously tells me that sure you can estimate sigma and theta through simple quadratic variation argument. The proof of this proposition is, in a sense, once you know the structure of the solution, it's done, and you use Kharionov law of expansions for Brownian motion. So immediately I will apply this previous result, and that estimator translates in the language of this new solution U of my heat equation, stochastic heat equation, as such that I have the central limit theorem, and these are the estimators. So for sigma, would it be the quadratic variation of U, time fixed? I'm sampling in space on very small interval AB. Assume that theta is known, and you have sigma, an estimator. And the more you sample, you will converge to the true sigma squared, and that's the rate of convergence is root of m. And vice versa, theta hat is 1 over that, and same results. So that's it for sampling scheme A. We've done, and it was quite, in a sense, simple. Now, if I sample in time, which is more interesting actually, if I fix x and sample in time, things are become a little bit dicey. First of all, the solution is 1/4 continuous in time, almost 1/4 continuous in time. So it's not a Brownian motion. It cannot be a Brownian motion. Maybe a fractional Brownian motion, maybe. But this 1/4 indicates that we probably should look at fourth power. And it turns out that indeed it can be proved that the solution U as a function of time for a fixed x can be represented as again a coefficient, and again this coefficient has exactly the parameters that I need, plus a process V times a process V that has finite fourth variation. The fourth variation is computable, it's 3D minus C, plus something infinitely small. And for this variation, we also have a central limit here. Okay. Now, this proof is not as simple as using a Kharionov law of expansion. The proof is semi-constructive. Then we use elements of Malavin calculus to show all the convergence rates. Then so-called the fourth moment theorem. So it's quite involved, but it's possible to prove. But once I have this result, of course, if I take the fourth variation of this, I'll derive immediately the estimators for sigma, and here they are. Sigma squared can be estimated, fourth variation in time now, well, root of it, and then, a correction term here, and vice versa for theta hat. But it's also interesting that we also showed, and for PD people that I hope you can appreciate, it turns out that the same estimators work if I'll take not bounded domain, not 0 pi bounded domain, but I will take the full space. And why I say that? Because the solution of a heat equation on the bounded domain on the full space is quite different. So the green function is different. One is heat kernel, another one is the sum of the signs, sine kx, ky. Okay, but the estimators are absolutely the same. So, and naturally this is true because, again, the nature of these estimators is quite local. And the local scheme doesn't matter what kind of boundary conditions we have there. That was a very particular case where I take, one-dimensional heat equation on bounded domain or unbounded domain, and with zero boundary, with zero initial data, and we showed that indeed the estimators conversion asymptotically normal. I derived them. What's interesting here is that the derivation of the estimators was more based on analytical properties of the solution, in contrast to going through the usual statistical procedures where you'll have perhaps start with a maximum likelihood estimator. Of course, in this case, it's not possible to do because this random field has complicated transition probabilities. And we did vice versa. So we ignored and we cooked up these estimators from using these power variations, and then we got the estimators. Now, the question is, what else we can do? So maybe a graph that shows that indeed everything converges where it's supposed to converge. So in the last several minutes that I have, let me give you a glimpse of what is happening in general. Okay, so this idea can be elevated to much more general SPDs. More precisely, I'll take this equation, which is sort of the first part is sort of the heat equation. It's still parabolic. I can take fractional Laplacian. You don't like fractional, take alpha is equal to 2. I can take a perturbation, a nonlinear perturbation. So this is a nonlinear curve, whatever that nonlinearity can be, and we have very general assumptions on this nonlinearity. Space is still gonna be 0, 1, one-dimensional X. I'll take a noise, again, space-time-wide noise, dWt, but I'll apply to this function, okay, well, stochastic process, I'll apply the Laplacian to negative gamma, and the same problem. I'll observe X by the same schemes, either in time or space, discretely, and I want to estimate either theta or sigma, and let's say sigma. So first of all, what this Laplacian does to this noise. So first of all, negative gamma is positive, negative gamma, that implies that this is an integral operator, right? So the inverse of the Laplacian would be an integral operator. An integral operator will smooth out the noise. If you smooth the noise, the PDE kind of analysis suggests that you'll smooth out the solution, and indeed this is true. Probabilistically speaking, when you smooth out the noise, you color the noise, where you put some correlation in a correlation structure in space. So the noise becomes more correlated in space, and more correlation changes completely the statistical properties. And in fact, it does not help. We like to have IID, independent, identically distributed random variables. At the moment they start to be correlated, things become hard. So this is exactly what this noise does. From applications point of view, typically you would like to have maybe something which is smoother and not space-time in both directions. I mean, not white in both directions in time and space. Translate it in analytical properties. So again, my heat equation, if I ignore the nonlinearities, this business does a simple thing. Since I know everything about this Laplacian, I know eigenfunctions, eigenvalues. Eigenfunction is sine k pi x, eigenvalues is k squared. That's exactly how this operator will work. It's diagonalizable. So it's not that big of a deal. You just multiply by k to the power negative gamma. Well, that means the Fourier coefficient decay faster. That means also that this part is smoother. That translates the solution is smoother. And that gives me a problem. So now, if I want to do the same trick that I did before, things will not work exactly as I want. Large gamma gives smoother solutions. Smoother solutions also means that I cannot take power variations now in X. And when I say smoother solution, I should clarify in X. In T, they cannot go more than 1/2 because Brownian motion is 1/2. Here I'm changing only the structure in X. In time, it's still white, and you cannot bypass. It will get smoother, but will not get smoother than 1/2. And I'm not going to talk about this because indeed in time, you can do what I did in the previous slides. I'm interested now to see what can I do by observing things in space. Power variations will be zero. Because the solution, once you have derivatives, you know, there is only variation, and variation doesn't give me anything. That's as there is no power variation. There will be zero, right? But I also know how smooth is this solution. So if f is equal to 0, that's how many derivatives I'll have. And again, that can be proved that I'll have 2 gamma plus alpha O2 minus 1/2. So alpha equal 2 would be 2 gamma plus 1/2. So the larger gamma, the more derivatives I have. Okay. So what do I do? And as I just said, it's not possible to apply the previous scheme because things will just be equal to 0. It's not it's a trivial variation. But I can probably take first derivatives. For example, m derivatives, where m is the highest classical derivative that I can take in X. Whatever this number is, gamma is fixed, whatever this number is, I'll take that many number of derivatives. What would be left? The fractional part of this, or fractional part of that, would be something, let's denote it by capital H from Hess parameter, and maybe it will behave as a fractional Brownian motion plus a smooth process. So fractional Brownian motion is a generalization of a Brownian motion that will have, memory. It's H bigger than 1/2 is smoother, H smaller than 1/2 is rougher, 1/2 is the Brownian motion. And I'll have a proper definition, but that's intuitively what is happening there. And indeed, we can show that this is true. And then I'm done, because once I observe this, I can use the same argument as before. The right power variation to take in this case would be, well, 1/h. So if h, let's say, is, I don't know, 3/4, take the power variation 4/3. And it's done. And it works. The only problem here is, and for somebody, of course, who does theory, that's good enough. Statistically, practically speaking, that's not satisfying, because that means I'm assuming that this process, which is the nth derivative in x, is observed, and that's not observable. Whereas I don't know experiments that observe derivatives of any order that I need. Okay, so what can you do? I said, but that's not a problem. If you know how to estimate using the derivatives, maybe you should approximate these derivatives by some schemes, for example, by forward or backward finite differences. And that's very natural. And actually, we tried to do that, approximate the derivatives with the measurements that you have, for example, by finite differences, but then it doesn't work. And it's interesting that actually when we've been doing first time, it says, yeah, sure, let's do that. And then numerically, we could see numerically that it does not converge. I mean, you dance around this code for days and months, and it does not converge. And all of then we realized that actually we've been doing a simple mistake, not mistake, but omitting one thing, what we learned 20 years or whatever years ago about numerical analysis. If you want to do finite differences, you better have one derivative there. And we don't. I mean, literally, we violated the assumption, the basic assumption, how the finite differences works. So, which means that things have to be changed. And in the last couple of minutes, I just want to convey the message that it's possible to find how much we are, by these approximations, how much bias we introduce into the estimates, and we've been able actually to compute that bias. So that's the latest results that we have. How do we do that? To do that, again, what we have to do is look at the processes which are smooth, for which we integrate this process. This J is integration. Delta H is the finite difference. We integrate M times, we take the capital M finite difference, and we look at these objects. Now, there is a theory behind that, and we use Zygmunt spaces and things like that. But eventually, what we figured out is that we need not simple power variations, but we need power variations which are properly rescaled. And there are reasons for that. Doesn't matter how they are defined. The point here is that you pick a power Q, you pick an index S here, and if this exists, this limit exists, we call it a generalized or delta power variation of order QMS of process S. It's more general than simple power variation. Okay, and I'm don't have time to go into details what all of these numbers mean, but literally we look at the higher order variations through also these increments or finite differences. Next. And I will conclude in literally, I'll show you a couple of more slides. I have 1 minute. What we needed to do is to understand how things are done for fractional Brownian motion. Once that is understood, the solution follows. And this is the main theorem that says that, look, if you take a fractional Brownian motion, okay, you integrate it m times, you apply this power variation, the limit exists, And this red bit, it's a constant, which is the correction that we've been missing. And it's a non-trivial constant. Later, once we know that, we can do for general SPDEs and looking at fractional Brownian motion plus something smooth. And we have general assumptions on how the regularity works and what is the optimal regularity and what should be those powers P and Q. We cover heat equation, reaction diffusion, advection diffusion equations, and so on. And the final result is, yes, you can estimate sigma. You need to make this bias, multiplicative bias, or this correction, and that's the central limit theorem. And now, indeed, when you do numerical computations, things converge as they are supposed to converge. Okay, and that would be my talk. And thank you very much for your attention.
Thank you very much.
Happy to take questions.
Question, comments, please. Apăsați. Da.
Bună ziua, domn Celencu.
Bună ziua.
Mă bucur să vă aud. Aveți, într-adevăr, ați avut un raport foarte interesant. La mai multe conferințe am fost martor la problematica aceasta, este foarte actuală. În special, de pildă, cred că cunoașteți lucrările domnului Barbu, dar puteți să le găsiți. Acum, referitor la întrebări. În primul rând, cred că vorbiți de soluții slabe, într-un fel, da? Fiindcă U aparține lui C, o pătrime în T și o doime în X. Corect, cred că, da?
Da, deci eu, să răspund în română sau poate în engleză sau cum?
Da, în română, dacă se poate.
Da, deci soluția, se definește soluția, să încerc eu să mă mut înapoi la slide-urile mele. Deci eu n-am definit soluția, mă rog, era mai mult focusat pe statistică, dar deci soluția se înțelege în următorul fel. Deci, din punct de vedere a ecuațiilor diferențiale, se înțelege ca soluție slabă.
Da,
Dar din punct de vedere, deci mai este partea a doua, este cum înțelegem soluția din punct de vedere probabilist. Deci din punct de vedere probabilist o înțelegem tot în varianta slabă probabilistică. Sau mai este varianta tare sau strong solution. Deci întrebarea e un pic mai delicată, dar într-adevăr, din punct de vedere a ecuațiilor e soluție slabă, din punct de vedere a proceselor e soluție tare în omega. Deci în X e slabă, în omega e tare.
Am înțeles. Da, mersi. Altă întrebare, dacă se poate. Așa înțeleg că toată ideologia asta merge și în cazul n-dimensional atunci când domeniul este, de pildă, un paralelepiped sau este o sferă, dacă așa e corect.
Aș vrea să spune da, filozofic da, practic demonstrațiile sunt mult mai complicate. Deci ultimele rezultate vreo 40-50 de pagini. Deci problema e că trebuie de controlat soluția foarte, foarte, foarte exact. Și reprezentările...
Adică și zic că acolo se poate construit în paralelepiped, de pildă bază la Paseanului.
Da, desigur, da. Da, în paralelepiped spate și sferă spate de construit exact cum la mine a fost sinus KX, exact așa spate de construit. Dar iarăși noi avem ceva de genul mișcare browniană asta fracționară, are niște reprezentări acolo care nu prea sunt clare. Deci sunt lucruri fine la nivel de probabilități cum se reprezintă procesele. Dar filozofic eu sunt sigur, ferm convins că asta e corect, că rezultatele sunt corecte în orice dimensiune, absolut.
Și ultima întrebare, dacă se poate. Deci, referitor la problema de control, în sensul următor, aveți ecuația asta, zicem, simplă, da? Condițiile inițiale date, aveți un timp T mare și căutați partea dreaptă în așa fel încât în timpul T mare să ajungeți la o stare care doriți dumneavoastră. Dacă sunt așa probleme studiate în cazul ăsta stocastic, fiindcă când nu e stocastic, sunt foarte multe.
Da, da, întrebarea e foarte complicată. Să încerc să răspund în română, în engleză mi-ar fi mai ușor, probabil, să spun. Deci, controlul la proces nu e ușor. Deci, în momentul când, și eu să încerc să explic și Viorel Barbu are acum o serie de lucrări pe tema asta. Deci, în momentul când încercăm să controlăm un proces, deci controlarea procesului, să spunem că vreau să au distribuția aia în viitor, e tare, tare complicată întrebare. Și de regulă se face prin, deci, stochastic control problem, să scrii pe urmă ca o ecuație de asta care se numește BSD, care merge înapoi. La procesele, la ecuațiile simple, timpul înainte sau înapoi e clar.
La ecuațiile parabolice nu lucrează înapoi.
Exact. Deci la ecuațiile parabolice una ca asta nu lucrează simplu înapoi, dar din punct de vedere stocastic apare altă problemă. Că noi informația se duce înainte, deci noi nu știm ce o să întâmple în viitor, deci noi nu vedem ce se întâmplă în viitor. Și acolo sunt acum în teorii noi cum se poate de rezolvat, cum lumea se uită la așa întrebări, dar nu e, cu alte cuvinte, stochastic control for SPDs nu e ceva care e ușor. Există stochastic control for diffusions, lumea a înțeles aia destul de bine prin ecuații de astea backward stochastic differential equations. Încearcă lumea să scrie acum backward SPDs și într-adevăr Barbu are o serie de lucrări împreună cu Rochlin pe tema asta, dar da, eu nu mă ocup cu asta. Dar întrebarea e foarte bună, da, mersi.
Mulțumesc mult, domn Celenco, și mă folosesc
de
ocazie. Vă invităm la anul la Universitatea să avem conferința 10-a ediție în luna iulie, începutul iulie, sfârșitul iunie.
Șansurile sunt mari că o să vină, așa că da, mulțumesc. Da. Cea mai mare plăcere, da, mersi mult.
Următorul raportor nu este conectat, Zelekovski, și o să fim nevoie să anunțăm pauză. Cu cine? Nu, putem, nicio problemă, dar eu din cauza asta n-am întrerupt. 40 de minute și încă 10 minute au fost. Până la referatul doamnei Ștlomiuc, 15-20. Da. Noi am verificat toate селele, dumnealui nu-i conectat la nicio sală. Он никакой не подключился, Зеликовский. У меня контакта с ним не было. Да. Дана Шлумюк. Да. А вот Николай Иванович говорил с ней только что. Да. Вазалану нету, и у него в почте ничего не было про Зеликовского. Igor, aici e liber, așa că dacă ai întrebări...
Da, mulțumesc, Florin, încă o dată, mersi mult pentru invitație. Da, mersi mult. Dacă mai sunt întrebări, cu plăcere răspund, dacă nu, revin.
Igor, salut! Valer
rog.
Teoremele limite centrală, dar aveți voi ceva despre viteza de convergență, rezultate sau nu?
Deci avem numai rata de convergență și mai mult la nivelul ăsta nu avem mai mult nimic. Pentru cazul care unii facem în spațiu Fourier, da, sunt mai multe, sunt minimax teoreme și chestii de astea, da. În cazul ăsta nu avem. Tot ce avem rata de convergență rădăcină din M, din număr și tot. Bine, și, da, central limit theorem avem, deci există asymptotic varianță. Da.
Mulțumesc.
Am și eu câteva chestii, vreo două întrebări. Una ar fi, vezi, ecuația căldurii însăși descrie un proces linear. Și dacă adăugăm la ecuația căldurii un noise, Brownian, a Brownian noise, why this kind of setting? It's not very clear. At least for me, I don't understand why this kind of problem appear. Is there some particular need of this equation? You see, you have an equation which describes a Brownian motion. And then you add to this equation a Brownian noise. Why?
Right.
What?
Right.
Why?
So yeah. So it's true. It's true that if you look at the heat equation, then
Yes.
actually the solution to the heat equation would be the density of the Brownian motion. That is,
Yes.
yeah, and that's how this heat kernel appears, and that's correct. But then you don't look in this way that it is sort of heat equation, propagation of heat already in an ideal gas or whatever ideal environment that you have over there, and then you say, well, this is the Brownian motion. No, the philosophy, I think, for SPDs, if you want to look from that point of view, is to say that, well, even if I have this ideal thing, perhaps it's not, there is environment which is random. There is things that influence that ideal law, how the heat is propagated. And then you can, of course, add the noise to, I don't know, to the coefficients or to the initial data. Or you can just say that probably it's something plus something random. So this is for the heat equation. What I try to look actually at SPDs is not from what PDEs mean from the get-go, but rather as a modeling tool. So if you take, I don't know, filtering equation, right? That's an SPD. And I'm just saying heat equation for PD people to understand that I can solve it numerically. I mean, I can solve it explicitly, and I know everything about that solution. From applications point of view, I think I'm more interested in things from finance, where we have these strange PDEs, which are random SPDEs. People look in, my friends from Germany actually have data from biology, where you have these strange diffusion processes, and you look at them and they resemble something that looks like heat equation plus noise, and then you just postulate that I believe that these molecules or these proteins are folding like that, and they do actually have real data, and they tried to apply all of this theory to specific data, and they have movies and show that you can actually measure, and these are big projects.
So as I understand, that means the problem comes from, might be other problems you have, problem.
Correct.
Correct. This kind of noisy equations comes from some problems. And
correct.
Okay, but then I have another question. So look, this kind of discretization of equations, certainly this is not for the first time. There have been already some works in this kind of problems. What is the difference from the previous? Is it true this is the second order term which appear in the right hand side, or what is the difference? Because I know a lot of work on the partial differential equations where they did this kind of theorems for the estimation for the coefficient, central limit theorems, and so on and so on. So this is not new. Look at the
I don't think so. I don't think so. So it's. I don't think they did for. I think that was the first time that when we did.
You mean where is the problem? The problem is this in the second order derivative, or what?
The problem is in observations in physical domain, okay? And the randomness. So second order derivative, yeah, it should be parabolic, but that's not that important.
Oh, okay.
What people did, yeah, for PDEs, people did a lot of approximations and a lot of things.
Mhm.
It's not, I don't think anybody did for stochastic PDEs driven by space-time white noise, physical domain. I think we've been among the first. And in fact, those two papers that I mentioned, they have been
I probably should object on this because I think that there are a lot of work with,
like what?
with this, maybe not this kind of equations. I wanted just to know what is the difference, but okay, if you say
So again, the difference is there is a lot of maybe I should be a little bit clear. So there is a lot of literature, especially from Russian school, on usual diffusions, on
what usual.
SDEs. Usual means stochastic differential equations. Okay, so and there is a lot of work on that. And of course the densities are coming from PDEs and so on and so on. And there are books, there is school, the whole, tons of books written on that. When we talk about infinite dimensional, there are fundamental, maybe, yeah, I'll explain if you allow me, I'll explain. When we talk about SPDs, and I'm talking literally PDE, which is an infinite dimensional object, plus infinite dimensional noise. Things happened, and it's not a translation from usual SD, stochastic differential equation, or stochastic diffusions. It's fundamentally different. And the difference is that you do not need to observe the solution for time going to infinity. If you take a usual equation, an SDE, and you try to estimate the drift, something in front of dt,
Yes.
you'll have to increase time to infinity. The ergodicity, this is how it works. There is no any way around. And the point is that there the measures are absolutely continuous to each other. You can do the Gersonov theorem, you can do rather Nicodim derivative, and then you can use ergodicity and you show, and you have to increase time. What people figured out, and this is not my result, Boris Rosovsky figured out some years ago, that actually for SPDs, they are so singular and measures are so similar to each other, you don't need to do that. And the results actually that I showed today is precisely very different from anything was before. You don't need to increase time. You don't even to increase space. You observe the solution locally a little bit, and you can estimate the coefficients. And this is fundamentally, that's actually a very good question. Thank you. Fundamentally shows that things are different. And whatever people did for diffusions, it's not translated here. So, yeah.
Okay. I understand. I should take a look at the paper. Thank you. Anyway.
Sure. Thanks. Great question. Yeah.
Jeszcze trzymam. Won, pieczkę. Absolutnie. No, pracować karę diferență.
Да. Я русская не знаю. Что она там?
Добрый день всем, раз пока никого нет.
Виктор Анатольевич, вы меня слышите?
Да, слышу, добрый день, рад вас видеть, поэтому и включился, чтобы посмотреть на всех вас. Как у вас дела?
Я хочу вас приветствовать.
Спасибо.
Я был на вашем докладе, мне очень понравился. Мы записали, будем его изучать.
Спасибо. Это сейчас совсем другая тематика, совсем новая.
Тут пытаются установить связь с
Кабелем,
Канадой,
да.
и поэтому такая...
Ну, поэтому пауза, я поэтому вошел, думаю, раз пауза, надо ее использовать. Хорошо.
Я очень плохо вас слышу.
Ну, что
Наверное...
делать? Большое расстояние.
А Зеликовский не будет представлять. Нет, он даже не связался с нами.
Понятно. Хорошо, ладно. Приятно было всех увидеть.
Извините. Тут
приятно
мешает.
всех увидеть. Хорошо, до свидания.
До свидания. Спасибо вам большое. Всего хорошего.
Всего хорошего также.
Хорошо. Да, știi.
Uite, m-am unmute. Da, acum s-a deblocat?
Da, s-a deblocat.
Start sharing. Am apăsat Start sharing.
Stimați colegi, continuăm ședința conferinței cu ultimul raport plenar pentru ziua de azi a doamnei profesor Dana Șlomiuc. O să dau citire titlului Algebrogeometric and Diophantine Aspect of Integrability in the Theory of Polynomial Vector Fields. Professor Șlomiuc, please.
Yes, thank you very much. I want to thank the organizer for having invited me to be present at this conference. I very much appreciate the group in differential equations from Chisinau, from the Institute and all universities in Chisinau, and I'm happy to collaborate with Professor Nicolae Vulpe. Next. I'm going to talk about the polynomial vector fields. These are produced by differential equation dx over dt is equal to p, dy over dt is equal to q, where p and q are polynomials with real coefficients. The vector field associated is p d over dx plus q d over dy. And the degree of such a system is the maximum of the degree of P and Q. And in particular, we call quadratic. In the case, the systems are of degree 2. Next. Polynomial vector fields are objects of a mixed kind. They are algebraic objects because they involve polynomial on the right-hand side of the equations. And of course, they are analytic because we involve differentiation. And the first question which arises is how much of this algebraic aspect impacts the theory of differential systems. And the partial answer to this question was given by Darboux in 1878. Next. In a seminal paper in 1878, Darboux gave a geometric theory of integrability based on the concept of invariant algebraic curve. This is a curve f of x, y is equal to 0, where f is a polynomial, and this is invariant if it's invariant under the flow. And in 1890, Poincaré expressed enthusiasm concerning the Darboux work, and he said the following in one of his papers: the road was opened by an admirable work of Darboux. And to stimulate work in this direction, Poincaré suggested the creation of a prize, and Paul Painlevé won the prize, and Léon Othon obtained a memorable mention. Next. In two papers, one published in 1881 and the other one in 1885, Poincaré launched his qualitative theory, and he considered polynomial differential systems. His motivation was because of the problem of the stability of the solar system. But the equations there being very complicated, he concentrated on simpler equations, and these are the polynomial differential systems. And the accent in his work was no longer placed on individual solution, but on the whole set of solutions in their whole domain of existence. Poincaré introduced many concepts, and in particular the concept of limit cycle. Well, of course, this is an essentially analytic notion. It is the limit of the surrounding solutions. And about limit cycles, in 1900, in Hilbert's lecture in Paris, he proposed a problem, namely the second part of his 16th problem, which is on these systems, and which asks for finding for every n the maximum number, h of n, of limit cycles for the real polynomial differential systems. And this is an essentially transcendental problem. This problem is still unsolved even for the lowest degree, n is equal to 2. Next. Now, so advances in Hilbert's 16th problem are practically non-existent, but there are problems arising from Hilbert's 16th problem, and there are some advances on this side. And in particular, the individual finiteness problem proves that a number of limit cycles of a polynomial vector field is finite. And we have two proofs, one given in 1990s, in the early 1990s by Ilyashenko and another one by Ekal. Smale commented in the year 2000, and he said the following: these proofs need still to be digested by the mathematical community. And recently, in 2023, in a Toronto mathematical meeting, Ilyashenko acknowledged that he found a gap in his proof. So at the moment, we only have just one proof, that the proof of Ekal. The problem was solved for quadratic system, this individual finiteness problem, by Ciccone, Schaefer, and Bamon. Next. We have other problems, and here is the global finiteness problems. Next. Can you, yes. Now, Darbous's interest was on complex differential system, on the complex projective plane, but since real systems are part of the complex systems, to a real vector field, we can associate a complex vector field on C2. And Darbou gave the formal definition for an invariant algebraic curve. This is a curve f of xy, where f is a polynomial, such that if we apply the vector field to f, the result factors through f. In other words, f, the derivative of f with respect to x times p plus the derivative of f with respect to y times q is equal to the product with f times k, where k is a polynomial with complex coefficient called the cofactor of f. Next. The basic theorem of Darbou is about integrability, so let us recall that a function defined on U with values in K, where K is either the real field or the complex field, is a first integral of the system if it is constant for every solution curve x of t, y of t for all t. In other words, if we apply the vector field to H, we get 0. And Darbou's theorem is the following: if we have a sufficient amount of algebraic invariant curves, let us suppose that we have m invariant algebraic curves, and if m is greater than n times n plus 1 over 2, where n is the degree of the system, then we have a first integral, which is of the following form. It is a product of the powers of f1 by raised to complex numbers lambda 1, lambda n, which we can find. So the system is integrable. Next. Next page, please. Now the proof is very simple because we can apply the vector field to fi, and this must factor through fi. So by using this identity, polynomial identity, we transfer the integrability condition into the sum of lambda I ki is equal to 0. This is a polynomial identity, which leads by identifying the coefficients on the polynomial on the left-hand side to 0, to a homogeneous linear system of equations. And because we have more variables than equations, then the system is solvable. So this function is called the Darbou function. In particular, rational functions, that means functions of the form f1 over f2, are of this form because we can write them f1 to the power 1, f2 to minus 1. And we call degree of f the number which is the maximum of the degree of little f and little g, the degree of g. Next. We call integrating factor function r such that if we apply the vector field to r, this factors through r. In other words, we get here a cofactor as being the minus divergence of p and q, and where the divergence is d over dxp, d plus d over dyq. And if we have an integrating factor, then of course we can ask for functions of Darboux type to be an integrating factor, and then we have a non-homogeneous system of equations in lambda I. Next page, please. Now, except for the papers of Painlevé and Othon, we also have two papers of Poincaré published in 1891, where he formulated a problem known today as the problem of Poincaré. For more than a century, no significant result was obtained in this theory. Thus, Darboux was well ahead of his time with his geometric theory of integration. Now, the problem of Poincaré formulated in 1891 is the following one. This is the initial formulation of the problem by Poincaré. Recognize when a polynomial differential system has a rational first integral. Now, this is a global problem. The system could be of any degree, thus the problem involves all the polynomial differential system, and clearly it must be a very hard problem. Next, please. And now, suppose that we have a rational first integral, then this must be constant of all, for all t, for any solution curves. And so the point x of t, y of t of a solution must lie on an algebraic curve f minus cg obtained by eliminating the denominator. So all the curves are algebraic. We obtain a foliation with singularities, and the degrees of these curves are bounded by the degree of the first integral, which is maximum of little f max and degree of little f degree of g. Next, please. Next page. Now, Poincaré argued that once we have a bound for the invariant algebraic curves of the system, then we can begin calculating by calculating first the lines and then the conics and so on. Because we have the bound, the process must stop at some point, and we can decide if we have or not a rational first integral. So the reformulation by Poincaré of his problem is the following. Is it possible to bound the degrees of algebraic invariant curves of a system in terms of the degree of the vector field? Poincaré's problem became known as the problem of bounding the degree of invariant algebraic curves of polynomial differential systems. Now, supposing we have a bound, then all we need to do is to compute the algebraic invariant curves. So, next, please. Next page. Then to find them, we just write the polynomial identity, saying that this is an invariant curve. And we reduce this by identifying the coefficients on the left side to the right side. And we find a system of equations which we solve. But this system is algebraic. If we look at the right, we have to multiply the coefficients of f, which are unknown, by the coefficients of k, which are unknown. So we will have a quadratic algebraic system of equation. And so we have a warning: the system could be difficult to solve even with the present day computers. Next page, please. Now, sufficient conditions for solving Poincaré's problem appeared only in a theorem given 1 century and 1 year after the the paper of Darboux, and namely by Joannou. And he said that if we have m invariant curves, and if m is sufficiently large, it is greater than or equal to n times n plus 1 over 2 plus 2, then there are integers n1, n2, nm, such that the product of powers of fi raised to these exponents ni, which are integers, is a first integral. Well, in this case, clearly such a first integral is a rational function because we can group the powers with positive integers, call this f, little f, and the powers with negative integers, and taking minus and I, then we have a function g, and so we have a rational first integral. So this is the first significant theorem that was given, and this was more than a century later after the work of Darboux, which was well ahead of its time. So next page, please. Then the best result obtained after this publication is by Karnicer. Ilyashenko and Diakovenko said in their book, Lectures on Analytic Differential Equations, that this is the strongest result. This paper was published in the Annals of Mathematics, which is the best mathematical journal. It is a very competitive journal. So the title of Karnicer's paper is The Poincaré Problem in the Non-Dicritical Case, which can be stated as follows. Let F be a foliation with singularities. Think of it as the foliation engendered by such a system with their singularities. But this foliation is in the complex projective plane. And let C be an invariant algebraic curve not passing through any dicritical singularities. By a dicritical singularity, we mean a singularity with infinitely many solutions, either ending or beginning at a singularity. Then we have a bound for these curves, which do not pass through any dicritical points. And namely, this bound is the degree of f. Think of the degree of f as being the degree of the polynomial system plus 2. So we have a bound for such system. Next page, please. Now we can comment that the theorem is both very general because it only involves the degree of f, which can be any number. And it is also very limited because we take just curves not passing through any dicritical points. As it is perhaps due to the generality that Ilyashenko and Diakovenko regarded this as the best result of this problem. But we should not ignore its limitations. Now, in the paper of Karnicer in Annals of Mathematics, no examples were given. And the first legitimate question which comes to mind is, what are the systems possessing phase curve not passing through any dicritical singularity? So we have to find some examples and perhaps a counter-example. Next page, please. In his address to the ICM, International Congress of Mathematicians, in 1900, Hilbert said the following: in dealing with mathematical problems, specialization plays, as I believe, a still more important role than generalization. Perhaps in most cases where we seek in vain the answer to a question, the cause of the failure lies in the fact that problems simpler and easier than a one in hand have either not at all or incompletely solved. So let us limit the problem. For the lowest degree of nonlinear system, it is for quadratic system of degree 2. And furthermore, let us limit ourselves to curves of degrees at most 2. Next page, please. For curves of degrees at most 2, we have a long sequence of papers obtained by Professor Wolf and myself, starting with quadratic polynomial system with invariant straight lines and followed up by quadratic polynomial systems with invariant conic curves. And we have 11 papers covering this last mentioned case. And these were written by Professor Wolpe, myself, and our 4 Brazilian colleagues, Dos Santos, Mota, Rezende, and Travaglini. In these papers, the configuration of invariant conics and/or lines were studied for quadratic system, and for some of them, the topological classification of the systems were given in the together with the bifurcation diagram in the full parameter space of the 12 coefficients of the quadratic systems. And this produced a wealth of examples for which to study the Darboux integrability of the system. Next page, please. Now, parallel to these developments, we have developments in the theory of Darboux. And namely, this theory underwent a considerable extension with the introduction of the concept of multiplicity. Let me give you here the main steps in the development of this notion. The first notion was introduced by Professor Wolpe and myself in 2004, restricted to invariant lines. So we defined what we mean by multiplicity of an invariant line. Generalization followed in 2007 by Christopher Ibre and Pereira, who gave 5 distinct definitions of multiplicity and showed that they coincide if the polynomial defining the invariant curve is an irreducible polynomial. But these definitions are proven not to be equivalent for polynomials which are reducible, and the proof was given by myself in 2022. Also, the concept of exponential factor, which is e raised to a rational exponent, was defined by Christopher in the 1990s, and who called it a degenerate algebraic curve first, but this is called now exponential factor. So if we apply the vector field to such an exponential factor, then what we obtain is factors through the exponential factor. Now let us denote by QSL greater than or equal to 4 the family of polynomial system which have invariant straight lines of total multiplicity greater than or equal to 4. This family is formed by 3 distinct families, those which have total multiplicity of invariant lines equal to 4, then to 5, and then to 6, because 6 is the maximum number. The maximum number of invariant lines that a polynomial system could have is 3n, where n is the degree of the system. This result was proved by Artes, Grünbaum, and Ibre in 1997. So for quadratic system, this maximum is 6. And then Professor Wolpe and myself proved the following theorem. We have 4 articles published between 2005 and 2008 on this topic. And namely, the theorem can be stated as follows. By affine transformations and time rescaling, the family QSL greater than or equal to 4 can be brought to 87 canonical forms, and modulo the group action, this family is 2-dimensional. All systems in this family are integrable, having an integrating factor of the following form. So we have a Darboux factor and an exponential factor, and this is the so-called generalized Darboux form. Next page, please. Now, if we consider in particular QSL6 with the total multiplicity exactly 6. By total multiplicity, of course, we mean the sum of the multiplicities of all the lines. And we have the following theorem. Modulo the group action of affine group and time rescaling, we have a total of 11 orbits. Any system in this family has an integrating factor of a special form, namely it is the inverse of a polynomial f of x, y. And we have a rational first integral, foliating the plane into conic curves. This family has a total of 11 phase portraits. Now, so we have examples where we can look for Garnier type curves. And of the 11 phase portraits which we have, only one has curves of the type in the Garnier paper. And the 10 others have no such curves. So this is a rather restrictive condition. Because in this case, we have a rational first integral, and Garnier detects only one case. Next page, please. Next page, yes. Denote by QSH the family of polynomial system with invariant hyperbola. Then we have a result published by Professor Vulpe, myself, Olivera, and Rezende, which says the following: by affine transformation and time rescaling, the family QSH can be brought to 26 normal forms, and modulo the group action, the family is three-dimensional. Now, these three theorems, which I mentioned before, provided us with a very rich set of concrete normal forms, so we can study their integrability, and in particular, the PhD thesis of Anna Maria Travaglini from the University of Sao Paulo under the direction of Regilene dos Santos and myself was completed in 2001 on this family, leading to two joint publications in 2022. And now let me consider some concrete examples. Here we have a system belonging to QSL6. Now this system is drawn on the Poincaré disk. This is the Poincaré compactification of the plane. And we can think of it in this way. Let us consider a sphere, and let us place our plane as being tangent to the sphere through the North Pole. And for every point on the plane, we join the point with the center of the sphere, and this line passing through the point and the center intersects the sphere in two opposite points, so we can project the whole plane on the upper hemisphere and on the lower hemisphere, and we have here two diffeomorphisms. So there is a theorem which says the following, that there exists an analytic vector field defined on the whole sphere, including the equator, which we may consider as our points at infinity, which is analytic and which has identical phase portrait with our projection from the plane on the upper hemisphere. So we obtained in this way the phase portrait on the whole upper hemisphere completed with the equator, which we can project vertically to the plane passing through the equator, the horizontal plane, and we obtained this phase portrait. Now here, except for the two saddle points, all the other points are the critical points, and all the solution curves pass through the critical points. So we have all the singularities of the systems are here, and we see that we have absolutely no curve to which we can apply Garnier-Serre's theorem. Next page, please. Now here we have two examples. On the left we have a picture belonging the class QSL4. So we must have four invariant lines. We see here only two, namely the vertical lines and the line at infinity, but we have two more lines which are complex line and which intersect at the focus on the right side. So we see on the right side that we have no curve that could be of Garnier type. On the left side, we have curves that could be on the Garnier type, but they are not, because they are not algebraic. If we compute the first integral, we see that we do not have any curve which is algebraic here. On the right-hand side, this is a picture that has a foliation into conic. So we have algebraic curves. So all the curves here are of Carnicer type. In particular, we have the vertical straight line. We have the line at infinity. And apart from that, we have 4 more lines, 2 of them passing through the center, which is inside the left side, and the other 2 complex lines passing through the center, which is on the right side. Next page, please. And now here 2 more examples from the class QSL5. So we must have on the left 5 invariant lines. Well, clearly here we see only 1, because we have the other 4 lines. We have 2 lines passing through the focus on the left side, and which are complex line, 2 lines passing through the focus on the right-hand side. Both singularities here are dicritical, so we don't have any curve which is of Carnicer type. And on the right-hand side, we see the same thing. All curves go or originate from a dicritical point. And here we must have 5 invariant lines. We see just 1 on the picture, but we see the vertical line and the line at infinity, actually 2. But the line at infinity has multiplicity 4. So a total multiplicity is 5. Next page, please. Now, let us go to the equation to see a little bit what's going on. On the left-hand side, we see the 2 complex curves that intersect at the focus on the left. We see that to annihilate the imaginary part, we have to make y is equal to 1 and x is equal to minus c. This gives us the coordinate of the point on the left, the focus on the left, and then analogously on the right. And if we multiply the polynomials that define these lines, we obtain a conic curve with real coefficients and another conic curve from the lines on the right-hand side. And if we multiply, we get here an integrating factor, so the system is integrable. And now we see that starting with complex invariant lines, we can obtain a real first integral. So we can apply to the real system the theory of Darboux in a very efficient way. Now, on the right-hand side of the preceding pictures, we had an invariant line which was x is equal to 0, and also a parabola, which is x squared minus 3y is equal to 0. And we have a rational first integral, actually a polynomial first integral, which is x times x squared minus 3y. Next page, please. And we have the following theorem concerning the QSL5 family, that modulo the action of the affine group and time rescaling, we have a total of 30 normal forms for these systems. 11 of them depend on only 1 parameter, and 19 are without parameters. And each system has a very special integrating factor, namely it's a polynomial inverse integrating factor, and the generalized Darboux first integral of this form. Now, all the invariant lines of the system QSL5 are not of the Darboux of the type of in Carnicer's theorem. So we have rather a large quantity of systems to which we cannot apply Carnicer's theorem. Next page, please. Perhaps the easiest way to illustrate both algebraic geometric aspects and Diophantine aspects is the following earlier result published in 1993 by Christopher and Coe. Namely, we consider K algebraic solution Ci is equal to 0, where Ci is a complex is a polynomial with complex coefficients. We give 4 distinct different conditions which are hypotheses from A to D. Let me state just one of them. the hypothesis B, no more than two curves meet at any point in the finite plane are not tangent at these points. These other three conditions, the first three from A to C, are about the way the curves intersect. And then we have a fourth condition saying that the sum of the degrees of the curve is n plus 1, where n is the degree of the system. Then the system has an integrating factor, which is inverse polynomial. We take the product and we take 1 over this product of the polynomials, and we have an integrating factor. Next page, please. Now, again, we can comment that this is a very general result because it is for an arbitrary degree n, but it is with very restrictive hypothesis. In fact, none of these hypotheses are necessary, as we have counterexample for each one of them. And here I give a counterexample for two of these hypotheses. We have this system defined by the polynomials x squared minus 1 and y squared minus 1. The degree is 2, so n plus 1 is 3. And we have these 5 invariant lines written here in blue, and the inverse integrating factor turns out to be the 1 over f1 to f4, which are the 4 lines. Now, this contradicts the hypothesis C, because the two lines f1 and f2 are parallel lines, which means that they intersect at infinity. So we have 3 of the curves, 3 of the lines that have a point of intersection, which contradicts hypothesis C, and analogously for F3 and F4. And we also contradict the hypothesis D, because if we take the sum of the degrees of Fi, this is 4, and it's only 3, the degree of S plus 1 is 2 plus 1. And we also can give counterexample. So next page, please. Then here it is interesting that we have a Diophantine aspect, because if we search for a polynomial L such that 1 over R is an integrating factor, this means that we can search for R in the form product of powers of the invariant, of the 5 invariant lines. We write the identity that will give us the linear system of equations, and then we ask Mathematica to solve it, and we get this general solution. And among this, we have lambda 3 coincides with lambda 2, lambda 4 coincides with lambda 1, and lambda 5 is equal to 2 minus lambda 1 plus lambda 2. This is a Diophantine equation. We have to solve it in order that R be polynomial for non-negative integers, and we have exactly 6 solutions. And one of them, namely 1, 1, if we have lambda 1 and lambda 2 equal to 1, then all the 4 lambdas are equal to 1, and lambda 5 is equal to 0. So this factor disappears, and we have this. So we have this Diophantine equation, which here is very simple, but if we go to higher degrees or for the curves or even for the system, and of course we would get lots of Diophantine equation. Next page, please. Now, Diophantine aspects intervened also in the problem of Poincaré. This problem was solved for the family QSL 5, greater than or equal to 5, by my student Pacom, Tab, and myself. And Tab is a student which I co-direct together with Professor Vulpe. And work on solving Poincaré's problem for QSL 4 is in progress. Next step is to consider the Poincaré problem for quadratic vector fields with invariant conics. This is a more difficult problem because we have numerous normal forms. And the solution for the quadratic systems with invariant hyperbola for some of the 26 canonical forms was given, as I mentioned before, by Oliveira, myself, and Anna Maria Travaglini. And in all these systems, we have very few. We have just 2 cases where we only encounter one line in each case, which is a cell-to-cell connection in both cases that satisfies Carnicer condition. All the other cases do not satisfy Carnicer's condition. Next page, please. So now we come to questions and problems that we can ask. First of all, can we generalize the result of Christopher and Coe, eliminating what seems to be superfluous hypothesis? A second problem, can we do better than Carnicer by finding less restrictive hypotheses than we encountered in his theorem? A third question, in what way does the geometry of the configuration of the curves and the geometry of the singularities of the system interact in various types of the first integrals? And finally, what is the relation between the multiplicity of an invariant algebraic curve and the multiplicities of the singularities located on the curve? We see that for every multiple curve, we have multiple singularities placed on the curve. So what is the relationship between these 2 types of multiplicity? And there are lots of other problems. Thank you for next page. Thank you for your attention.
Thank you very much, Professor Shulmuk. Question, please. Comments. Thank you again.
Can I ask on the internet?
Thank you very much.
Okay, I have a question. Can I ask?
Yes.
Okay, question is the following. I am crazy in subalgebras, as you see. And have some subalgebra structures in your problem? For example, easy question. If you have first integral for f of g,
Can you speak louder, please, because I don't hear you?
Okay. Do we have some algebraic structure? For example, if I know that for f of g and have polynomial f of g, I have first integral, can I say the same, for example, if I replace them f square and g square?
I didn't understand the question. The communication is not very clear.
Okay, you have polynomials. You have 2 polynomials here at the starting point. For example, f of g, so for your system. And it's good. Suppose it's good, you have your first integral, whatever you want. And after this, can I replace, for example, f of g by f square and g square? Still will be good, or we lose all properties?
I'm sorry, but the communication is not very good. I cannot understand the question.
Okay, no problem. Okay. But thank you for nice talk in any case.
Sorry, maybe you write to me and then I can answer by email.
Okay. Bye.
Thank you very much, Professor Shulmuk. Thank you.
Thank you.
Pauza indicată.